Let us start the class for today. We'll be discussing the recap of the classes for the reaction chemistry of some alcohol and the related functional groups. So reactions of alcohol and related functional groups, and we'll briefly discuss the part of aromaticity. Okay. So let us start. So as you know, alcohols, they typically have the chemical formula, some group, and then OH, and their property pretty much resembles with water. So for example, you have the simplest of alcohol, that is ethanol, okay, or isopropanol. So these are called 1 degree or primary alcohols, and this is called 2 degree. And if you have something like this will be the tertiary alcohol. And what are the physical properties of alcohol? So they are very much H bonded. And this will be intermolecular interaction. So because of having this electron rich oxygen as well as the proton, so they will typically have this hydrogen bonding between themselves. And this way results in more viscosity and higher boiling points, okay, like that. And we have to discuss the chemical reactivity. Reactivity of alcohols. So in general, they can, you can consider these ones as both acidic as well as basic nature. Okay, how? Let's see. But to react alcohol with something that is more, basic than it itself. So then what will happen? I will get CH3O minus, and it will be stabilized by the sodium plus, and you will get NH3. So this is much more stable than your alcohol. So here in this case, alcohol is giving away this proton. So it is behaving like an acid. Whereas if you react this one with extremely acidic substance, very much acidic substance. For example, you react methanol with HCl. What will happen? This oxygen, it has lone pair, so this lone pair will go and abstract this proton, so that you will have CH3 H2 plus Cl. So you can see, depending on the reactant, it can show both acidic as well as basic nature. Now, what about the reaction perspective? So, suppose one nucleophile you have, okay, and then you have your CH3 and H. If you simply think of that, you will attack the nucleophile on this carbon and this which will leave. So this is not possible. Why this is not possible? So this will be no reaction. Which minus not good leaving group, right? So what we need to do in this case, we need to convert it, okay, to a certain species that is more, readily, more ready to live, okay, more good reacting living group. So in this case, we generally do it by protonating the oxygen, okay. So what you can do, if you just take some acidic medium here, then you can have CH3 OH2, it will be positive, and then any nucleophile can attack here and remove the water. Okay, plus you have this CH3X or something. Okay, so this is a good living group compared to OH minus. You have many other ways to make this OH minus to a good living group, so we'll discuss it. Uh, but more systematically, let us start. So first we'll go through the synthesis. The ways that we can synthesize the alcohol. So we have already discussed from starting from alkene, you can use the acidic medium so that you will get the hydroxylated product. You can use boron chemistry, BH3THF, and second step you need to use the peroxide so that you will get the regioselective hydroxylated product. Okay, I'm not showing the proper stereochemistry here, but for the moment it's fine. Then you can have oxymercuration demercuration reaction. You can end up with the alcohol. Then also what you can do, you can react any alkane in the acidic medium. Okay, so that you will end up with the more substituted hydroxylated product. You can even think of some substitution reactions, say for this very preliminary alkyl bromide. Can use one nucleophile so that it will go through an SN2 mechanism and then we'll end up with the desired alcohol. So this one for primary alkyl halides, it will proceed through the SN2 mechanism. But if you have the tertiary alkyl halide, in that case, it will not go through SN2. Rather, it will go through SN1 because it will form a stable intermediate carbocation. Okay. And then in the second step, the nucleophile will attack and you will get your final compound. So now let us go through the reactions of alcohols, right? So Alcohols typically are very reactive, very much reactive. Okay, so with the electropositive metals, it can react, such as if we use sodium, and in pristine form, it is in zero oxidation state. So it will form this sodium alkoxide, and it will release hydrogen gas. Okay. So, in the laboratory, if you have tried to quench sodium, unreacted sodium somewhere, so you will see that always it is use some kind of alcohol. Okay, isopropanol or ethanol. Sometimes we have to use so that you can quench the unreacted sodium. So this is the general practice. Then, as already told you that this OH we have to convert it to OH2, which is a good or better living group. Say the reaction of an alcohol with an acid, how it will proceed. So you have this electron, it will follow an SN2 mechanism. So that first state OH2 plus, and then your Cl minus, it will come, it will attack here and remove the OH2. So that you will get to your desired compound. So the next reaction, we have to see that reaction with PBr3. PBr3 is a widely recognized brominating agent. Okay, so how the reaction goes like, so phosphorus is a family of nitrogen group, and this is the typical structure. So which will come here, it will attack on the phosphorus side, then leaving the bromide, and what it will form, positive on oxygen, and then Br, Br. So here you will have delta minus and delta positive, so that oxygen will attack on the phosphorus center. Okay, so now what you have to do, you have the bromine minus bromide can attack here. Okay, and you will get your desired compound. So one thing to notice here is that if you react, this is primary alcohol. So if you react 2 degree or 3 degree alcohol, okay, so the scenario will be different, right? So then we move to another reaction with SOCl2. So this is also called as thionyl chloride. Very much known reaction, and we generally do it in lab scale. So generally you can convert 1 degree or 2 degree alcohol to its corresponding chloroalkane through this reaction. So how it will proceed? You will have your alcohol like this, and the structure for SOCl2 is something like this. You have two chlorine singly bonded to sulfur and one double bonded oxygen. and this lone pair of oxygen will go to sulfur. It will attack here. You have some lone pair here. It will go back and actually removing one chloride. And in this reaction, pyridine is used as a base. Why? So this part will come in the second step. So you have the proton on oxygen with a positive charge. So something needs to abstract this proton in order to stabilize the system. So in this case, pyridine will do this job so that you will get. Okay. And now your chloride will come and remove this chloride again. So you will have your product. One gas is formed, that is sulfur dioxide and Cl minus. So this is the driving force for the reaction to proceed. So this is gaseous. Okay, this is readily released from the system, and that is why this reaction proceeds to the right side or the forward direction. And this step is SN2, rate determining step. So similarly, we can look into another compound that is called sulfonyl chloride. Sulfonyl chloride. So sulfonyl chloride is generally of the form of is RSO2Cl. Okay, so generally, typically there are two known compounds. One is called tosyl fluoride. Maybe many of you have heard it, or simply we call it as TSCl, which is nothing but CH3. Then you have a phenyl ring. Then yes, double bond Cl, and other one will be methyl chloride or MSCl, CH3 plus double bond Cl, right? So generally the reaction will go through like this. CH3. So we'll definitely have the pyridine here. Okay, it has to abstract the proton on the OH. So this OH then plus. This is lone pair, it will abstract this one and will get to your stable intermediate. Now finally your minus will come here. So what we'll have, we'll get your desired compound here plus minus. In this case, this sulfonyl anion, so this is much more stable uh, due to many resonance structures. Okay, that is why the reaction moves to the forward state. And then, so one of the key advantage of these reactions is, you can get the exact stereochemistry that you want, from the starting materials using this technique. So just for example, you have this compound which is of special stereochemistry, say R. You want to convert it to the another enantiomer, that is S. Okay. So you generally can think of like you should have some living group here. Okay. And then some nucleophile or which will come and just replace this so that you can get your desired product. Okay. But if you use, in this case, if you use SOCl2 here, you will get the chloride on the opposite position, right? So this will be of no use. Okay, so what you need to do, you have to use this docile or methyl fluoride so that which let's say we're using methyl fluoride. Okay, in presence of pyridine, then I will form this intermediate. With this one PSH. If you attack with nucleophile in this case, and you will get the similar stereochemistry, not the opposite one, your desired stereochemistry. Yes. So for the intermediate, if you use these docile or methyl groups, you can have the similar stereochemistry from your starting material. So that depends on your desired product and how you can utilize it. Let us move further from here. Briefly discuss about the dehydration reaction. So if you react with concentrate sulfuric acid with an alcohol, so what will happen? This is the structure. This oxygen lone pair, it can take another proton here, so that you will get this electropositive hydronium charge, and this can eliminate from here. Okay, this will be an E1 mechanism, so that you will get your carbocation on the more substituted carbon center, so that it is stable. And then the next step will be you will have one proton here, so H2O. In the medium there is always H2O. This will abstract the proton and we will form the stable alkene. Okay, so with that, let us move towards the oxidation of alcohol. Okay, so we need to we need to keep in mind that if you oxidize, so there are three type of alcohol: 1 degree alcohol, 2 degree alcohol, 3 degree alcohol. So if you have no constants, you are using one general oxidation like oxidant. So what will happen? 1 degree alcohol will go to the aldehyde, and it will not stop here. It will go further to the carboxylic acid. If you are using 2 degree alcohol, it will stop at ketone. But 3 degree alcohol, generally you cannot do the oxidation. Okay, it will not oxidize, no reaction. Right? So what are the oxidation agents that we use? Reaction with H2Cr O4. Okay, this is called chromic acid. This is a typical oxidating agent for alcohol, and this is also called as Jones reagent. Hmm? Mm. You have a general alcohol like this, and if you treat with Jones reagent, will form the so 1, 2, 3, 4, 5, 3, 4, 5, the aldehyde, but it will not stop here. Okay, it will go to the carboxylic acid. This will be your end product. But if you need to stop at the middle, like the first instance to the aldehyde, you need to use some controlled oxidation. Okay, to control the oxidation, you need to use some mild reagent. What are the mild reagents that you can use? So you can use PCC, which is called pyridinium chlorochromate. Okay, so we use PCC, exactly end with the aldehyde. It will not go further. So with that, alcohol part is over. So we move on to thiol. History of SH thiol. Yeah. So if you need to compare between the alcohol versus SH. So difference is in the oxygen versus sulfur, right? So sulfur has inner d orbitals. It is much more bigger in size, and this angle it deviates from this is typically around 100. That deviates from the ideal 109 degree 5 minutes, right? So what are the things that we need to know here is SH bond less polar than OH. Why? Because oxygen, see, sulfur is much more bigger in size, so it can accommodate electron, much easily. Okay, or it can stabilize the electron, and that is why it is not that much electronegative. Okay, the electronegativity of sulfur is less than oxygen. Okay, so in this case, this bond is less polar, so that is why the acidity If you think of acidity, thiols are more acidic than OH. Why? Because this RS minus is very stable than RO minus. Because of the bigger size of the sulfur, it can accommodate or stabilize the electron. Now, let us check how we can synthesize the thiols. So similarly, like oxygen, like the alcohols, you can do SN, nuclear substitution reactions. Like you have a living group here, and simply if you use on attacking nucleophile, so that will generate the thiol. Okay, that's all about thiols. Uh, Next is ethers and oxides. So you generally know about ethers, so they typically have the form R, O, R prime. So sometimes these can be equivalent. Both R groups can be same or it can be different. Okay, it can be symmetric as well as asymmetric. So let's say for this one, CH3O, CH3, this bond is almost same. Okay, for the sp3 case, and this is symmetric, whereas this is asymmetric. And these ethers established organic solvent any reaction. And epoxide also three-membered ring consisting of an ether linkage. Okay, this is also called oxygen. We'll just discuss them in few minutes. So let's start with the synthesis of ethers. First reaction is called Williamson ether synthesis. Yeah, maybe probably all of us have had this reaction, and let us see. So have a epoxide that is attacking on a primary, alkyl halide. Then you can synthesize. So this mechanism is SN2 mechanism. H3 plus I minus. Okay, this is 1 degree. Now, why it should be 1 degree? If you have something like 2 degree, if you have 2 degree, 3 degree alkyl halide, let's then the reaction is let me get it. Okay, because in this position the attack is difficult. If you try to attack in these positions, this will be much more difficult. Okay, just a second. So the next reaction will be acid base, not cations. Acid catalyst and dehydration to ether. So you have the alcohol here. You react with concentrated H2SO4 at 100 degree. You will get plus water. So how the reaction will go? You have the lone pair here, and it will form the uh, positive charge hydronium, and then you will have another oxygen molecule or the alcohol, and that can attack here, so that you will have this one. Just let me check this file once. From here, what will happen? You have H2O that will abstract this proton, and you will get to your product. Okay. Next reaction will be, we will react some alkane with the alcohol in presence of acid. So what will happen? So this will take the proton and form the stable carbocation here, and you have CH3OH, okay, that you can get. So H and CH3 positive. This one will help you to abstract the proton and get to your product. Okay. So let us discuss some more reactions. If you reacted with concentrated HBr or HI, what will happen? First, it will take up the electron. This oxygen will take up the electron so that you can form this positive charge species, and then whatever Br minus in this case, it will go and it will form these two compound H3Br plus H. Okay, so thing is to note that only HBr and HI will react in this case, okay, not the HCl. And if you have some more stable ether, like having 2 degree or 3 degree groups, in this case also you will get H plus Br. Okay, so let us start the discussion on epoxides. Also, it is called oxygen. Okay. So, as already I discussed once, it will be a three-membered ring consisting of oxygen. If you look into carefully, epoxides are much more reactive compounds. Okay. How you can form an epoxide? So, starting from an alkene, if you use Br2 and water, you know that it will go through a bromohydrin formation, so bromonium ion first and then reaction with water, so that you will get one anti-product. These are all discussed, and we'll treat it with a base, okay, so that the proton will get abstracted. We'll get this one. Now this is of interesting thing. So if you really give it like how the molecule will look like, so it is a cyclohexane. If you draw it in 3D in the chair conformation, these are having trans, okay, trans relation, and this oxygen now it can go and attack to the antibonding site of the CBr bond, and it will go, and then what it will form this one, right? So you can see that only trans will form the epoxide, not the cis form. Okay, only trans will form. Next reaction is reaction with MCPV. Okay, MCPV is a special reagent, okay, that reacts with alkene and forms the epoxide. Huh? This is called metachlorobenzoic acid. So the structure is like metachlorobenzoic acid. Okay, if you react it, will form the epoxide. Okay. So this mechanism you don't need to know at this stage. Let us move with the next reaction, which is acid catalyzed ring opening. So ring opening of epoxide. So as I told you, epoxides are very much reactive. So this ring opening is very important reactions in any series of reactions or any chemistry that concerns with the epoxide. Okay, ring opening. What you can do, if you have a simplest of epoxide here, you can use acid, any acid. Okay, and it will take up the proton with a positive charge, and then water can attack here. The water can attack in any position, so that we'll have right. And eventually, if you work up, it will give you one glycol product. So now thing is, depend on the stereochemistry. You can have starting material like this, or the other way. You will end up with a trans diol. So we'll end up with a trans diol. Okay, so this was acid catalyzed. Similarly, you can have base catalyzed also. Say if you have this one, you are reacting with the base. Water is already in the medium. So base will generally attack at the less substituted position. Okay, and it will form the anti product. As a whole, if you have an alkene, you can react it with a MCPBA to get a syn epoxide. Later, you can get the trans diol. On the other hand, if you think of using another reaction which can give you the cis oxidation, we will get to the cis product. So it all depends on how you want your product to be. Depending on that, you can choose the reactant. Okay. With that, we complete the reaction part, and there is one more part left, which is called aromaticity. So you already all have heard about the aromaticity. So benzene. This is the very preliminary aromatic ring. Okay, but this aromatic term and this notion took so much time to get acquainted with. Okay. So for benzene, you have the degree of unsaturation. Saturation is 4, which is for 3 double bond, okay, plus 1 ring. So benzene typically has this structure on 6-membered ring planner, but thing is that this double bond they can interchange the position. Okay, these two are similar structure. So this is called actually resonance, and the resonance hybrid is generally represented as like this. Okay, so there are some typical anomaly, like what you expect from a conjugated double bond and from benzene. So there is some extra stability, due to this aromaticity. So for example, if you know, we already discussed this part. If you use bromine in presence of DCM chloroform anything, you will have the dibromination product, which is an anti-form. Okay, but for benzene, if you use similar reaction condition, there will be no reaction. Okay, and if you use this bromine with little bit of catalyst, then it will react, but not all the position, just at one position. Okay, it will be like a substitution. Then for normal alkynes, you can have this dehydrogenation H2 EDC. It will give you dehydrogenated product. But for benzene, it doesn't work. But if you need to, get the reaction done, you have to apply some external pressure or external stimuli. This pressure you need to give 300 atm. Then it will react. So basically, all these things that indicates that this benzene ring, it has much more stability. Okay, so typically benzene has more than 150 kilojoule per mole. Okay, less energy than theoretically predicted extra high in. Okay, so the reason behind this is the aromaticity. So if you try to draw the molecular orbital, there is a special way of drawing. You have to draw a circle that will fit the polygon. Okay. So in this case, we'll draw with another color. These are the nodes. And then on each corner, you will have your energy levels. This is one, this is one, this is one, this is one, this is one. This can be noted as psi 1, psi 2, psi 3, psi 4, psi 5, and psi 6. So how many pi electrons do you have? You have 6 pi electron, right? So you can fill it like this: 2 here, 1, 2, 2. Now you can see you have filled all the orbitals. And one more thing I forgot to mention here. So this line that goes through the center of the polygon and intersects, bisects this circle, so it is called the non-bonding. Below this non-bonding level, everything is bonding, and this is called anti-bonding. So this is the reason that all these electrons stay in the bonding, and this is the reason for the stability. Okay, so Eric Hückel tried to do multiple calculation for different structures and to find some reason for this extra stability. So he came up with some rules that are mainly depicted as Hückel rule for aromaticity. What are the rules? First rule is that system should be planar, and the system should be planar. Second rule is each atom should be a p orbital. And third one is when first of two are satisfied, then you have two conditions. One, if you have 4n plus 2 pi electrons, it will be called as anti-aromatic. And if you have 4n pi electrons, this will be called, sorry, this will be aromatic if you have 4n plus 2. And if you have 4n pi electron, this will be called anti-aromatic. So let us just see some example just for benzene. How many? So it is a planar system. All of the carbon atoms are having sp2. Okay, so one of the p orbitals in are coordinating for the pi bond. So sp2 carbons having p orbital, and third is you have 6 pi electron. That is very much matching with 4n plus 2, n equal to 1. Okay, so this is aromatic. Say for cyclobutadiene, this structure. This is planar, right? This is sp2 having p orbital. But now in this case, you can see there are total 4 pi electron, and that means 4n. If n you consider 1, this will be considered as anti-aromatic. Anti-aromatic. What is the difference between aromatic and anti-aromatic? So these are much higher in energy, anti-aromatic. So maybe you are not able to synthesize this compound, or it will be very much reactive. So let us see one special case for cyclo octa tetra in. Okay, typically this looks like cyclooctatetraene. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so how much is the total number of electron? So this is 1, 2, 3, 4, 8, 5. And that is nearly coming around 4n if n equal to 2. Okay, each atom are sp2 hybridized, so each has sp orbital. So generally, with our general notion, we can think of it being an anti-aromatic system, right? But actually, it's not. Okay, because the primary thing is system is not a planar system. Okay, so this ring is not planar. So actually, due to large number of carbon atoms, it is staying like a puckered shape. This is generally like this. Okay, so this is not a planar system. That is why it is non-aromatic. Okay, so let us see some examples for heterocycle. So heterocycles, where you have some, in the aromatic ring, you have something that is not carbon, apart from carbon, maybe oxygen, sulfur, nitrogen, something like that. So we can discuss some examples. One is this pherol, okay, each, and one is pyridine. First, we need to see that this nitrogen, it can use this lone pair, okay, so that can have resonance structures. This will be minus. Now you can see here, this is planar, this is sp2, sp2 nitrogen. How many electrons do you have? 1, 2, 3, 4, and here 5, 6. So 6 pi electron, that is 4n plus 2, and this test system is aromatic. For pyridine, if you consider, it is similar to benzene except that it has a nitrogen in one center instead of carbon. Okay. Now you can see nitrogen has a double bond connected, but it has also a lone pair. So we should consider this lone pair or not. General rule is that when nitrogen is already have been actually fulfilled. Let's see. Here, don't consider the lone pair, right? In this case, we should not consider the lone pair because the thing is like uh, nitrogen, it is having two sigma bond with carbon, right? These are carbon, carbon. And then it will have one empty orbital where this lone pair is resetting. This is also sp2. Now it has one more orbital, something like that. Okay, where it has the extra charge. Okay, so, and this is participating in the pi bond. So it is already participating. You don't need to consider this one. This is not participating. So without considering that one, if you see it is planar, okay, then pi orbital, and then how many? 6 pi electron. That means 4n plus 2. So this will be aromatic. Okay. So now let us practice some of the questions. Just a second. Yes. So this is from the practice set for this week. First question says that is the following molecule aromatic, anti-aromatic, or non-aromatic? Okay, so you have to understand here. So it is carbon. So I'm just showing you here. Carbon, it has two orbital that is participating with the sigma bond. This is carbon, this is carbon. Now you can see here it has another orbital here where it is having the negative charge, and one more orbital on the tops up and down where is having the extra charge. So either can be lone pair or the negative charge, and this one it can use it in the pi bond. So this is sp2 hybridized. Okay, this is not participating. Right, so we can consider this one. You can also draw one resonance structure. So if it come here, so what you are having here, you are having 1, 2, 3, 4, 5, 6. So planar p orbital present, and then 6 pi orbit, 6 pi electron, that is equivalent to 4n plus 2, and so we can call it as aromatic. So this one will be right answer. Next is the following molecule aromatic, anti-aromatic, or non-aromatic. You can see clearly that this carbon it is sp3 iodide. Yes, and so it is non-planar. So when it is a non-planar, it is not going to be aromatic or anti-aromatic, so it will be non-aromatic. Okay, I guess you understand. Then what is the major product of this reaction? MsCl. Okay, what we have seen that whenever we are using the MsCl, we are getting the intermediate product on the same side. Then NaN3 is attacking. Okay, so I will just write it. First step, you will have minus and then H, and now NaN3, N3 minus, N3 minus will go and attack. Okay, and so that you will have N3 and then H. So what is the answer? So this will be 2. This one. Next question, what is the major product of the following reaction? So you are using concentrated H2SO4. So that means in the first step, it will be protonated and it will be H2 plus. Okay. And now you are heating it. Okay. This one will remove from here. Okay. Then you will have positive. But you can see you have a proton here that can migrate to this position so that you'll have much more stable carbocation present. Okay, then you have a proton here that can be abstracted by water, H2O. This will form the stable alkene. So what will be the answer? This will be first one. Okay. Next question, what is the major product of the following reaction? One equivalent of each I they have used. So first thing we have to see what it will do. It will take up the proton, which plus. Now let us see. Okay. Now it can cleave in two ways. First thing is if it cleaves here, then we will have which plus here one positive charge. If it clicks here, then we will have which plus here positive charge. So what you can see, this one is much more stable compared to the carbocation on the sp2 hybridized center. Okay, this is not stable. So obviously I minus will come and attack here so that you will have this third butyl iodide and this alcohol. So what will be the answer? 4. Okay, this will be the right answer. Now let us move forward. What is the major product of the following reaction? So you are reacting with PbR3, okay, in pyridine. So we have already discussed, right? Let us try to do it. First step will be the replacement of which by beer. Okay, I'm not going into the stereochemistry of this reaction. This is not required. Second step, they have used sodium ethoxide. Sodium ethoxide, what it will do? You have one proton here, so OET is a base. It will abstract this one, and so that it will be a SN, not SN2, E2 elimination. Okay, and you will have this product. Okay, you will also have one proton here. You have also one proton here, but this will not give you the stable product. Okay, this one is minor. This one will be major. This one will be major. So this one is the right answer. Second question is, which of the following molecules is not aromatic? Okay, first thing this. So here you have one each. Okay, so this one pyrrole, you know it is aromatic. Okay, you have furan. Furan is also aromatic. Now you can consider these two. Okay, let us just draw it. So carbon, you have one H here, you have two lone pair here. These are forming the sigma bond, and then you have one perpendicular minus charge, and this is participating in the ion. So this is conjugated. Compared to this one, the middle one, just draw it. But here you don't have any electron. You don't have any electron. This is vacant. Okay. So it cannot participate in the ion. So here the conjugation breaks. So this is not aromatic. This is aromatic. Okay. This one will be the answer. Next question, the product of the following reaction sequence is tosyl chloride. You know, it will be formed at the same site, same no stereochemistry. Then Na3. I know we already have done this kind of reaction. Just answered. Then it will be this one, 3. Next question. So the product of the following reaction is, this is, comprising some of the earlier class reactions also. So Si alpha to SiA to BH, okay, the hydroboration reaction here. So you know that first what it will do in the less substituted side, this boron will attach. Okay, so the first product will be this side will be H, and then when you are treating with in a OH H2O2, then it will convert to the OH. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. So this can be tautomerized. Okay, this can tautomerize to the aldehyde. Okay, and then you are oxidizing it to the carboxylic acid. 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6 OH. So just let me see 1, 2, 3, 4, 5. Yeah, this one would be the answer. 3. Major product of the following reaction is sodium ethoxide. Okay, so it has to form an epoxide. So first, there will be one elimination because we'll have this H here. Okay, this can take and you can form one alkene. Then you are reacting with Br2 water so that bromonium ion formation happens. We will get one bromohydrin product, right? So it will be trans. Let me just draw it once to your chemistry. Now you are giving base. Base what will do? It will take this proton so that you will get one minus charge generated. O minus, and you will have Br here. Then it will go and form the epoxide. So that we will have this. Not only that, you will also have the other product also because I initially started with one. So if this is on the top, then your epoxide will be on the down. So both the 1 and 2 can be possible. So 1 and 2, this one will be right answer. Next question, which of the following molecules are anti-aromatic? Okay. So this one, 2, 3, 4, 5, 6, 7. This is a special kind of cation. This is called tropylium. Tropylium cation. This is very much stable and this is aromatic. Why? Because this proton is somewhat lifted from the top. Okay, this actually stays like this. So that these other protons, it will actually become a planar system and it will have 6 pi electrons. So this is aromatic, this is benzene, this is aromatic. This is pyridine also aromatic. So this one, you can see this is planar, p orbital present. And it has 4 pi electron. That is 4n. So this is anti-aromatic. So 3 will be the right answer. Next question. Which one of the following compounds is obtained by the oxidation of tertiary alcohols by Jones reagent? Tertiary alcohol. Do they react? No, right? So 1 degree alcohol will get to carboxylic acid. 2 degree alcohol will get to ketone, but 3 degree alcohol doesn't react at all. Okay, so they do not oxidize. Next question, which synthesis will lead to the desired product? Any idea? See, uh, this OH and this group are anti to each other. Okay, so we have to use the tosylate or mesylate groups, right? Because they will initially form the intermediate in the same side, and then you are reacting with the one additional nucleophile, so this will attack from the back side. Okay, so this one will be C and D with the right answer. For A, PbR3, initially it will go to the other side, and when you are uh, attacking with another nucleophile, it will come to the same side. It will, so at the end, you will have both same side. Same for this one also. So these two cannot be the right option. Now, select the appropriate reagent to achieve this transformation. Okay. So how will you, proceed in this case? So this is an epoxide ring opening. Okay. And then what you can see, uh, this one and these two stereochemistry are opposite. Okay. So in this case, you need a base. Okay. So right answer will be this one. So let me just draw it. If you use the MEO image plus minus, this will straight away attack in the less substituted position. Okay, so that you will get to have this. Yes, this one will be on the back side. ME, and you have this 3OH. Okay, this can give some proton so that you will get to your product. This is an base assisted epoxy ring opening. Right. Next question, rank the following in increasing to decreasing acidity. Most acidic to least acidic. Now just check this functional groups what are present. OH, then SH, SO3H, and again SH. So in this among these four, you can see sulfonic acid. They are much more acidic, right? So C will be the top. Then you have two SH. You know that SH is much more acidic than OH because of the bigger size of the sulfur. Okay. So in this SH and in this SH, you have one electron withdrawing group. Okay. So if negative charge is on the sulfur, it will stabilize.